intelligence. So what I'm gonna tackle during this part of the module is basically computer science and their relation with mostly with the human mind, let's say. And then on Wednesday, I will be talking, I mean, if we don't reschedule this, I will be talking about machine learning, a very high level overview. And well, today I'm gonna start off by presenting you one of the main characters of computer science, which is Alan Turing. You see him here. Nowadays, I mean, computer science has grown exponentially since then, but I find it amazing how, you know, from a single and very simple idea, we now have this whole bunch of stuff today. So today I'm gonna basically present his main idea, which was that of an abstract machine. Okay, that has a lot to do with some of the stuff Heikel was talking about. So he already mentioned Al-Khwarizmi and Leibniz, because they the idea of a decision process was central already in their line of thought. And then in the pre-Turing era, I also wanted to mention Charles Babbage and Ada Lovelace, who are among the, well, they basically built one of the first computers. And Ada Lovelace in particular is still considered sort of the first programmer of the history, which is quite funny because, you know, the first programmer of the history was a woman, right? Nowadays, programmers are sort of nerds and men usually, but yeah, the first programmer was a woman. Then we have what I call the Turing era. So the idea of Alan Turing and the idea that was in the air, especially in the 1930 till 1940, was that of trying to formalize the concept of what it means to calculate, right? And all these people contributed to this, to working on this concept, so answering the question, what can be calculated mechanically, in a way. And then we have John McCarthy, Marvin Minsky, and Noam Chomsky, which may sound more familiar to you because they're more recent. They are the 27 gang, because they were all born around that date, and they developed mainly what is now known as artificial intelligence, and they're really important. We'll talk about more them in the next lectures. So Alan Turing, I don't know if are you familiar with him, by the way? I mean, apart from the movie, was that the first time you've ever heard about Alan Turing, or because I mean he's had a really interesting life, I think. You know, he was gay and had a really sad death. But anyway, I find it impressive that in just 3 articles, basically, he founded 3 fields. So it's not like, you know, nowadays that we all have to publish hundreds of paper to survive in the scientific community. He was able, you know, just with 3 articles to found. So in the first article, the one from 1936, he founded computer science. I think that's it's easy to argue that. In the 1951, he founded artificial intelligence. And then, well, I mean, in the 1952 paper, he was talking about what is now known as a Turing pattern, which is which finds applications in medicine. But I mean, so this is just to give you the picture of a very of a highly hybrid person. He was a hybrid as well, right? He had interests in biology, maths, physics, and whatever. And so what we're going to talk about today is especially his first article. So the idea underlying his first article. So if I look for if I search for the term mechanical on the Oxford English Dictionary, I find this. So it's, well, I like when it says often disapproving, done without thinking, like a machine, right? But what's a machine? At that point in history, there was no clear idea of what a mechanical process was, right? Because I mean, yeah, there were machines, but it wasn't really clear what how general they were, what could be calculated without any thinking. And this is, I mean, I'm simplifying it here, but this is what Alan Turing was trying to address. So he started out by asking himself, what are the possible processes that can be carried out when we compute a number, but we're trying not to think about it, right? So when we carry out multiplications, he was actually thinking of himself as a schoolboy doing the classic arithmetic operations, and he was trying to abstract from that, because I mean, you don't really have to be clever to do a multiplication like this, right? So his main idea was, well, let's take inspiration from a child's arithmetic book and let's think about ourselves. So he wasn't really thinking about machines, about mechanical devices. He was thinking about a person who was trying to carry out a calculation without any thinking involved, really, okay? So he thought, well, we all have finite memory. I think we all agree on that, right? Well, potentially infinite amount of paper available. You know, yeah, probably this sounds a bit weird, but it makes sense. Come on, I mean, if we are rich enough, we can buy paper and pens, and we can go on doing our calculation until we die, basically, right? So it's the second assumption sort of makes sense. And then he says, well, we have a limited field of view and action. We can clearly only act locally. I can't really, use telepathy or anything. So according to these ideas, he came out with the idea of a tape. So because he was thinking, well, yeah, children usually have 2D paper, But that's not really a strict requirement, because whatever I can do on a 2D sheet of paper, I can do it on a 1D tape of paper. Yeah. On a 1D tape. Yeah. So do you agree with that? Or does it sound weird? Do you think it's reasonable? So he's saying that any calculation that we do on a 2D piece of paper, he says we can just do them on one-dimensional paper. So
Yeah,
does it make sense to you? Okay, because not everybody would agree with that. It's kind of weird, but yeah, let's say that we accept that. He doesn't go on justifying this idea much in the paper, but yeah, let's say that this is reasonable. Okay, so according to him, so to carry out a mechanical calculation, we need a tape divided into squares. Okay, good. And he says, well, we all set of symbols. Sorry, can you hear me again? I think my connection. Oh.
Yeah.
Okay. Yeah. Perfect. So, yeah, he was saying, well, we can also fix a set of symbols. So we can assume the set of symbols that we can use is actually finite. And again, do you agree with that?
But sorry, but the intuition is like we have to imagine like that we have to work with the simplest condition.
Exactly, with the simplest, yeah, exactly, yeah. The simplest setup ever.
So one dimension, like a string.
One dimensional, okay. Yeah, like a string, exactly. And then also with, we would like to write symbols on this paper, but what type of symbols? So again, he was trying to simplify, and he says, well, let's assume we can only use a finite set of symbols. Do you find that reasonable? Because again, this is not really intuitive, I think, because for example, right, we can invent a whole, well, potentially infinite number of symbols, but he puts this restriction. He says, well, our alphabet is finite. And why is that? Well, because he says it doesn't matter, any symbol that we can invent, even in the future, can be thought of as a string of these elementary symbols that we've fixed. So there is no loss of generality in assuming that we only have a finite set of symbols. Okay. So he says, whatever, just pick one. Pick just 0, 1, or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or the entire alphabet, or the entire Chinese alphabet. As long as it's finite, it's fine. Yeah, so in this sentence from the original paper, he's summarizing what I just said. And then he also says, well, I can, oh, sorry, I just had some other examples here, but anyway, yeah, they can even be abstract ones, right? Doesn't matter. Or even, so a possibility is to use one symbol sometimes. But that's more of a special case, I would say, okay? Anyway, let's say that we start, so we only use the usual digits, and that we can put them on the tape. So, for example, we can write stuff like 91 or any number that we want. And then he says, well, actually, we are fine. Telepathy is forbidden. So, and also our sight, that's also limited. So we can only look at one symbol, and we can only change one symbol at a time. So he says, well, let's assume in this case, for example, we're only looking at the number 9 on the tape. What's left to model? Our state of mind. This is a first connection with theory of mind, because when we carry out a calculation, we are to some extent aware of what we've done during the calculation. So we know which actions preceded, so the steps preceding a given decision and any point in time throughout the calculation. So he says, well, let's assume we also have a finite set of states in which we can find ourselves in. And that basically our decisions, so our actions, depend on just on the state of mind and on the symbol we are looking at. So whenever we have to decide what to do next, we can only rely on that, on those two things. And this is because also he says, well, our brains are finite, so we can't really have an infinite number of states. Okay. So he took inspiration from the human mind when he came up with this. And so the point is, now we have to decide what the actions are, right? So when we decide to do next, what are these decisions that we can take? So he says, well, we have, again, without loss of generality, we can have a few, just 3 actions, basically. One is move right. So I'm reading 9. I just move to the cell on the, I'm moving from the 9 to the cell on its right. Move left, clearly, go back to the initial digit. And then what else? At any time, I can change I can write a new symbol on the cell I am looking at. Okay, and he says this is all you need. So it sounds a bit naive, but this is what, in a way, led to building the first computers, because he then went on studying the properties of these simple computers, and then he started showing that it's possible to capture and to solve interesting problems with them. Okay, so for example, I would like to do this little exercise with you guys. So suppose that we have a natural number. Okay, so a number like 41, and we want to multiply it by 10. So we want to simply do this, right? 41 times 10 equals 100. And let's assume that we start off with the input 41 on the tape. So this is the input. Okay. Well, yeah. Well, nowadays we would call the input of a program. So we are given 41. It's written on the tape. Somebody wrote it for us, and then we assume that we are looking at the leftmost cell of this input. How would you multiply this number by 10? Do you have any guesses? It's just using those three actions that I just described. This is also for me to, to understand whether I've been clear enough or or maybe not. So we are looking at 4, right? We can only move right or left. What would you do?
Well, the easiest way should be to move to the right until I'll encounter an empty space, an empty spot, and then place a 0.
Perfect. Exactly. So basically, this is a procedure that works, that always works, right? Regardless of the number, right? If I have another input, like, I don't know, 1074, if I want to multiply it, I can just follow this procedure, right? And what are the required states of mind in this case? So we only have 2. And why is that? Well, because we start off in I'm calling the initial state S0. This is just by convention, okay? So we always start with S0. And this state, in this case, is just saying, well, so the program that I'm following is saying, as long as you are in state S0, move to the right until you hit a blank cell, right? So whenever you encounter a blank cell, just change that blank cell to a 0 and change the state of mind to SF. So I'm calling it SF because that means that the calculation is over. There is nothing else to do. So I would call SF a final state. That just says the calculation is over, is finished. Okay. So we can try to formalize this this simple example, and so this is what people would call a Turing machine, which is a set of rules that tell us what to do whenever we see a symbol and we are in a given state of mind. Okay. So what this table is telling us is when you are looking at a symbol 0 and you are in state S0, just move to the right and stay in state S0. Okay. And the same for 1, 2, 3, 4, 5, 6, 7, 8, 9. You just move right. Okay. It doesn't really matter because you want to reach the end of the string. When you see a blank, so you don't see anything, and you are in state S0, write 0 on that cell, and the new state is going to be SF. Now, since there is nothing I can do in state SF, I assume that's a final state. So my calculation is over. Okay. So this is this looks really complicated for a program that just multiplies a number by 10, right? But this is what the initial intuition of Turing was. So let's take a look at another example, which may even sound more, less complicated. But it turns out it isn't. So let's find a procedure where we want to add 1 to any number. Can you help me with that? So how would you do that? It's very similar to what you said, Simone. So again, I would say
you have to move right.
Yeah.
But let's see, when you find the blank box,
yeah,
you have to go back and change the number.
Exactly. So I go back.
Yeah.
Right. So at this point, notice that when I move back, I change the state. So I was in state S0. I go back, and this reflects exactly what you said, Beatrice. So I'm changing to a new state that tells me I need to increment the current number by 1. Okay. So whenever I'm in state S1, I change that number and then move to SF. Okay. And at that point, the calculation is over. Is that clear?
Yeah, I have I noticed that if you have to generalize this calculus, you should need a third state. If you have 9.
Yes, exactly. Yeah, so you are absolutely right. And this is what the purpose of my next slide. I have 2 slides that are exactly the same, but anyway. Yeah. So this is the program to sum 1 to any number. So again, here I was trying to be short. So I had 9. So sorry. Any symbol from 0, 1 to 9, just move to the right and stay in state S0. Okay. So this is the state you are talking about, Simone. S2. So because in these cases, so if you're in state S0 and you see blank, you just go back, move to S1, which means if I can, I add 1 to the current symbol. If I cannot, I replace it with a 0 and move to state S2. So, which is the new state. So in these cases, I just have from 0 up to 8. I just write that number plus 1. So here I have 5 whenever I see 4, for example. Whenever I see a 9, I change it to a 0 and go to S2. Now, what? So, do you agree with the last line as well of the program? Do you see the need for it? This line here. Because even when I was writing this, I thought it's a bit tricky in a way. Because yeah.
So it's saying just do the same stuff you did before with
Exactly.
state S1. And in the same way, if you have 9, you have to do the same jump process, to the left. Right? Yeah.
Exactly. Again. Yeah. Again. So I'm just saying, well, in state S2, I just have to repeat the whole thing again with the number on the left. And this is why we have this line here. Okay. Perfect. So, and then I go back to S1 because that's exactly what S1 does. It adds 1 to the more significant digit. Great. Okay. So now, in his original paper, Turing was thinking of computable numbers. So this is so if we go back to so the name of the publication, it is on computable numbers with an application to the Entscheidungsproblem. So, so he was thinking in terms of numbers. So what numbers can be calculated mechanically? And this is especially interesting. Why? Well, because we have infinite sequences of numbers. Sorry, of digits. So, for example, real numbers have infinite digits after the dot, as in the case of pi. So he was trying to think, well, is, for instance, pi a computable number, or maybe not? What would you say? Do you think it is, or it is not? Would you say, I don't know, because this is when things start getting a bit complicated. So, yeah, tell me if you want
to. How is defined computable?
Computable, well, this is, okay, so this is the question that Alan Turing was trying to address, right? So he was saying anything that I can calculate with a Turing machine is computable, right? So he's trying to give a definition of computable. So he was saying, as long as I can find a program like this that outputs that number, I'm going to call that number computable. That's a computable number. Okay. So, I mean, it's kind of trivial for finite numbers. All finite numbers are computable because I can just think of a procedure like this one that simply outputs one after another all the digits of that finite number. It's going to probably be a huge program depending on the size of the number, but as long as it's finite, I have a Turing machine that outputs it, right? Because I don't know, let's say, is there any algorithm that outputs 432? Yes, there is, because there's an algorithm that outputs 4 when it's in state S0 and then moves to the right, then prints 3, and then prints 2, and then it's done, right? There is nothing clever about it. But when we go to infinite numbers, the thing gets a bit tricky, right? So we want a program that one after another outputs all the digits that are contained in pi. So let's say that I have I want to ask my program, well, give me the 100th digit in pi. And that program needs to output the 100th digit in pi. Okay. And it's an infinitely long sequence. So this is equivalent to saying, well, is there any algorithm that outputs the whole of it? What's your guess? I mean, it's.
Sorry, can you repeat the question?
So, do you think that there's is there any program or any Turing machine, in other words, that outputs pi? So all the numbers. So pi is a number that continues.
Yeah.
After the dot. Forever.
You won't have a final state, right? So if it's okay with that, I think.
Well, yeah, but you can translate this problem into a finite one, right? As I just said. So I can translate this problem into that of saying, can you give me the nth digit of pi? And would you be able to give me a program for doing that? So, I mean, it's not intuitive, right? It's because we were starting to tackle the problem of infinity in a way. But anyway, I mean, as I wrote here, yes, it is possible to find a Turing machine that outputs precisely pi. Obviously, I can't really provide you with such algorithm, because it is possible. I can promise you, and there are people who have written this this algorithm for a Turing machine. So they provided these rules to calculate pi. But for example, yeah, we could use this formula that approximates the pi. And so if we find an implementation of that for the Turing machines, then that means that pi is computable. So yes, since it's possible to find such an algorithm, pi is computable. As I was telling you, there are many other people, Emil Post, Alonso Church, and many others, Kurt Gödel, who came up with other concepts that are very similar to this one. Well, they were mathematicians, so they weren't thinking about machines really. They were thinking about functions, but they were trying to capture the same concept. What can we effectively calculate? And these are some of the formalisms that that they came up with. And you can look at the so the last one is particularly interesting because we can think of all modern programming languages as the grandchildren of Turing machines in a way. Okay, especially Ada. Ada is I don't know if you're aware of it, but it's named after Ada Lovelace, the first programmer in history. So this is really interesting because it seems that if we take Python programs, I don't know whether you are familiar with programming. Have you ever tried programming something or not?
I tried, but I abandoned soon.
Oh, okay, great. Okay, now that's good anyway. So you can sort of understand some of it, right? So basically, what's the point that I'm trying to make here? The first program here is a Python definition of the first Turing machine we saw. Okay. The second one is a Python definition. Sorry, this is the second one. That's the second example we had. This is the first example we had, and the third one. So this one is an algorithm to calculate pi. So if you just open a you just copy and paste this into Notepad and run it using a Python interpreter, that will give you as an output an approximation of pi. Okay. As long as this number is big enough, this number defines the precision up to which I want to calculate pi. I will get an output in a reasonable amount of time. Okay, so since so this is another point of Turing machines. We're all allowed infinite time to carry out computations. Okay, so we're working under that assumption. So it doesn't matter. Some programs, they could even take years to finish before they come to an end, but come up with a result. But it doesn't matter as long as we are concerned. We are allowed infinite time in the world of Turing machines. So there is a pattern here, because it seems that for each Turing machine in the examples, we were able to build an equivalent Python program. And I have a few questions for you here again. So do you think this is always the case? So do you think that given a Turing machine, I can always write a Python program that is equivalent to that Turing machine? What's your insight about this? What do you think? Is the question clear?
Yeah, probably.
Okay.
In any case, we can have a Turing machine. There is no issue in writing an equivalent Python program, also out of the mathematical process.
Exactly. So your answer is yes.
Yeah.
Yeah, exactly. How would you do that?
Well, if we don't have let's say an algorithm like the Leibniz algorithm, we can simply write in Python a Turing machine,
Exactly. So you can
a list of outputs and inputs and so on.
So you mean, well, you can simulate a Turing machine using a Python program, right?
Yeah.
Yes, exactly. And this was one of the biggest ideas that Turing had. I'll show you later on. So, and what about the other way around? So do you think that given a Python program, can I always find a Turing machine that simulates that? Yeah, so that is equivalent to that Python program. Or, I mean, it could even be impossible, right? In principle.
Well, if we can write a Python program, it is based on a Turing machine, meaning a computer. So it's quite tautological, maybe.
Well, basically, no. Well, it's not, because you can write a Python program that simulates a Turing machine, but can you then write a Turing machine that, given any program written in Python, gives you the translation into that language, the weird language that we defined before? So basically, given this, let's say, can I use this to find a set of rules of this form to that will give me the same output as this? It's not tautological, because I'm asking you, I want that to work for any Python program. So is this clear, right? So
I have a doubt in this question. That is, maybe I'm wrong, but when I think about a computer, I see it as a complex version of a Turing machine somehow.
Yes, you're right. Yes, you are.
And this is the key point of my tautological.
Right. Okay. Yeah. Well, you have to think that it wasn't tautological at that point in time, right?
Yeah.
Because all these formalisms that they had, they didn't really know whether they were equivalent or not, right? So they didn't know at that time. So if imagine that at that point in time, somebody came up with Python as one of those formalisms. So in 1936, without having any computer, right? So think of Python just as a mathematical object. So I guess that your point is, anyway, yes, you can find a Turing machine that simulates, right?
Yeah, but from the point of view that you are saying, probably the answer is not, because there are some non-computables operations.
Exactly. So this is the point. So is there anything? Sorry, can you still hear me? Because I'm having some. Okay.
Yeah.
So yeah, you're making the point. So is Python able to do anything that a Turing machine can't do? So obviously a Turing machine, I'm not, so the name machine is a bit misleading, because think of a Turing machine as a programming language. So do you think that you can write a Python program for which there is no Turing machine equivalent? So that you can't compute with a Turing machine, as I described it? You said no, right?
I don't know, actually.
Okay, that's fine. So the answer is yes, it is always possible. And this is so basically Python and Turing machines are two equivalent formalisms. And clearly also the others. So yeah, the short answer is yes. So sometimes when we have a formalism and we prove, sometimes even programming languages, we say that programming languages are Turing complete when they are equivalent to a Turing machine. So in the theoretical computer science community, there is a lot of talking about this. So when you build a new computer programming language, sometimes you want to make sure that it is Turing complete. Okay? And this really, I think this is really interesting, right? Because all the formal definitions of mechanical calculation seem to converge to to this concept of a Turing machine. So in this diagram, there are many formalists, including Python, including the others that I shown you, so the lambda calculus and so on and so forth. And these are all equivalent to each other, which is quite impressive. So it seems that all the people who tried to formalize the concept of a Turing machine ended up with more or less the same concept. So with the same definition. And this was formulated by Alan Turing and Alonzo Church in 1936. And they found it out together in very different contexts and terms. So Church, again, was thinking of mathematics, while Turing was thinking of it in terms of machines. But they came up with the same exact definition of computable numbers, if you like. Okay. So at this point, it's interesting to ask, well, can we explore this space further? So is there anything that is less powerful than a Turing machine? Well, yes, this is, I'm gonna give you the answer now, because if you limit a Turing machine, if you cut out some of the possibilities that a Turing machine has, you can find new classes of problems a new class of machines, so of algorithms that are not as powerful as a Turing machine, meaning that they cannot solve some problems that can be solved by a Turing machine. So there are some problems in here, in this space here, that belong to the wider space of problems that can be solved by a Turing machine, but cannot be solved by these other machines. So one example is that if, for example, we restrict the tape of the Turing machine to finite length, we get the set of finite automata. So there are some things that Turing machine can do that finite automata cannot do. And this is particularly interesting because that means that there is some way we can restrict the power of Turing machines. We can obtain less powerful machines, okay? The interesting question at this point is, well, is there anything outside the green circle, well, the green set? So is there anything here in the red bit? And this is was precisely the purpose of Turing, because he wanted to show, to answer the question, is there anything that we can't really calculate? And again, I would like to collect your guesses. It's what do you think? Are there any operations? It might be hard to think about one, but do you think that there are things that, so problems that a Turing machine or any other program in the world doesn't have an answer to?
Anything that includes randomness?
Yes, I would say so. I mean, don't think about that because it's a bit misleading, but I would include that in the set of possibility. For now, think of anything deterministic, by the way. And then we can talk more about the randomness, because it's a really interesting question. So can you define a problem for which nobody can write a Turing machine which can give an answer to it. It's hard, so I'm not expecting you to do very informed guesses. But anyway, the point is, yes, he was able to show that there are some problems that can't be solved by any Turing machine. And the point of his paper was showing that one of these problems, which is now known as the halting problem, is one of them. And he proved that this problem can't really be solved by any Turing machine. That was kind of a letdown, because the hope at that point in history, well, not anymore because of Gödel incompleteness theorems, but it was that maybe there was some mechanical procedure to solve any possible mathematical problem, let's say. Okay. Turns out there are some problems which you can't really tackle using a Turing machine. As I said, this is kind of similar to Gödel's incompleteness theorems that you may have heard of. And I just wanted to give you an idea of what this theorem looks like. And we're going to talk more about this in the next lecture. But it's the technique that Turing and others followed was very similar to trying to formalize the liar's paradox, which says that this sentence is a lie. And the key point of this is something that Simone already said, right? So you can write a Python program that simulates a Turing machine, right? Which is really impressive, right? Because that means that since Turing machines are equivalent Python programs, that means that you can write a Python program that simulates something that can simulate a Python program. And this is the idea that sometimes it's called the universal Turing machine, and that is at the heart of this word here. This sentence is a lie. So this sentence is talking about itself. And Alan Turing showed that it's possible that to write Turing machines that simulate Turing machines. So whenever you talk about, for example, in this case, this sentence is a lie, which doesn't sound very formal, he was able, using the concept of a Turing machine, to make this statement very formal. So he was able to to make Turing machine refer back to themselves. And using that mechanism, he was able to get a result, so a negative result that says that there are problems that can't be solved. Now, the whole point of this presentation was to make you think about uncomputable problems in the end. And the relationship of that these problems has with human minds is very relevant to cognitive sciences, because we can think of the human mind as one of these formalisms, and we might want to think, well, are there any Turing machines that are equivalent to whatever a human mind can calculate? And this is a very important point in artificial intelligence, and it's always been a huge problem in cognitive sciences since they were born. Okay, guys, so I'm actually done with the presentation for today.